All right. So what I plan to do today is basically finish up on chapter 4, and then in any time that we have remaining, we could use that for the purposes of review for your upcoming test. All right. All right. So let me okay. So let's talk about significant figures. Now, basically, when we're talking about the significant figures in a measured value, this applies to measured values. We are talking about those figures or digits in a number that we are certain about, plus other digits that we are not certain about. One other digit that we're not certain about. So let me just write this down here as a definition for significant figures. Okay, so the significant figures in a measured value are those digits that we are certain about plus one estimated digit. All right. So basically, whenever you're doing any measurements, right? And this is something that is very often misconstrued by non-scientists. Whenever you're measuring anything, it's at best an estimation. There's no such thing as an exact measurement. And the main reason why is because of the human element that comes into making any measurement. Because when somebody is making a measurement, there's always that possibility of some error being made by that person, all right? And the level of precision is reflected in the number of significant digits that is expressed in the measurement. So usually what happens is that when you're taking a measurement of something, and it doesn't matter if it's mass, length, whatever, then you're certain about some digits in the measurement, but there's one digit that you have to estimate, and that is the last digit, right? So the combination of those digits that you're certain about plus the last digit is what we call those digits collectively significant digits. I want to get to another, hold on. Okay, there is an example I want to show you. Now I have to go to another here. Another document, where is it? I think it's here. Okay, this is from another course, but this will apply to what we're talking about here. Okay, so this is the example I want us to look at. So let's say you're given a task of measuring the temperature of something, right? So you get these readings here. Now, let me just explain something. These are all thermometers. And if you look at this one here, you see that you have 20 here, and you have 30 here, and you have 10 equal division, right? So that means that this line here represents 21, this represents 22, and so on and so forth, all right? We have a similar type of scale on this thermometer, right? But this one is obviously different because not only do we have these larger units, but we have these smaller lines as well. So basically each of these lines represents, the smaller ones, represents 0.1, right? So for example, this line is 20.1, 20.2, 20.3, and so on, all right? And that will make a difference in terms of the level of precision that is being expressed in their measurements. So let's look at this one here, right? And let's say you're asked to write down the temperature being represented in this case, right? So basically, based on the scale that we have to work with, we know that the temperature is 21 point something, right? Because you have 20, this is 21, but the mercury level is above the 21 mark, right? So we know it's 21 point something. So the question is, what is that something? What is that digit that you'd have to place after the decimal point? So that digit, we have to estimate, right? We don't know what it is for absolute certain. We have to estimate that digit, right? So one person could look at this and say, well, I think it's 21.2. Another person could look at this and say, no, I think it's 21.1. As far as I'm concerned, both persons are correct, right? Both persons are correct because.
Figure C shows.
What's that?
Figure C shows it's at 22.
I'm sorry?
Figure C shows that it's at 22.
No, I'm not talking about this. I'm just
Yeah,
focusing.
the line itself. If
Yeah, what I'm saying is, I'm not talking about this one right here. I'm talking about this one,
A, okay.
what the measurement here represents. So one could say 21.2, another person could say 21.1, and they're both just as correct because even though we're certain about the 21 part of the number, we're not certain about the digit that comes after the decimal point. So in truth and in fact, it's actually 21.2, but as I said before, another person could reasonably say that it's 21.1, right? So basically, we are certain about the 2 and the 1 here. We are not certain about this 2 because it's an estimate. So therefore, collectively, the total number of significant digits here is 3, right? The 2 that we're certain of, plus the 1 extra digit that we have to make an estimate about, all right? So therefore, there are 3 significant digits being represented here. Now, if you look at this scale here, as I said before, it's the same scale as before, but this line here, or I should say the mercury, seems to be exactly at the 22 line, but it's not enough for you to say 22. You have to express the number of significant digits to the same level of precision as we did here. So therefore, we have to say that in this case, the temperature being estimated is 22.0 degrees Celsius, right? So again, we have to make sure that this is expressed to 3 significant digits because we're estimating the digit after the decimal point, all right? So in both cases, the temperature would be expressed to 3 significant digits. Now let's look at this setup right here. As I said before, there's 10 smaller divisions between the 20 and 1, right? So if we look at where the mercury level is at this point, right? This looks like 22.1 something, right? So the question is, what is that digit that comes after the 1, right? Somebody could look at this and say, well, this looks like 22.11. Another person could look at it and say, no, I think it's 22.12. Again, both persons, as far as I'm concerned, would be just as correct because while we're certain about the 22.1 part of it, the digit that comes after the 1, we're not certain about. So in this particular case, the temperature being estimated is 22.11. We are certain about this 2, we are certain about this 2, we are certain about this 1. What we are not certain about is this digit because it's an estimate, right? So therefore, in this particular case, the number of significant digits being represented here would be 4 significant digits, right? So this is just illustrating how we determine the level of significance in terms of the number of digits that we would get directly from an instrument like a thermometer that we're using to measure, in this case, temperature. But we can apply this to other types of measurements as well. The key thing here is that you need to recognize that every measured value is at the very best an estimate, right? That's the key thing right here. Everything that you measure is an estimate at best. There's no such thing in science as an exact measurement, all right? So that's a key thing you need to remember here. And basically, what we try to do is try to express our measured value to the highest level of precision that we can. And the way we do that is record to the correct number of significant digits, all right? So let me get out of this here and go back to the original PowerPoint. So what we're gonna look at are situations where if you're given a question and let's say you're given a measured value, how can you tell what the number of significant digits are? All right, and there are some rules for that which are listed right here. First rule is that in any measured number, all non-zero digits are significant, right? So if I give you a measurement and there are non-zero digits in that measurement, then those non-zero digits are significant. So for example, if you're given 1.55 grams in a question, then you should recognize that this number has 3 significant figures, all right? Now, the next rule has to do with zeros. In fact, all the other rules have to do with zeros in different situations. So in this case, we're talking about the zeros that are embedded or sandwiched between non-zero digits. And all zeros that are sandwiched between non-zero digits are significant. So for example, 1.003, in addition to the fact that 1 and 3 are significant, these 2 zeros are significant because these 2 zeros are sandwiched between 2 non-zero digits. So therefore, the total number of significant digits here represented is 4. Okay, the next one has to do with trailing zeros, right? And okay, let me see the best way to explain this. So if you have zeros at the end of a number, and if there's a decimal point anywhere in that number, then those zeros at the end are significant. All right? So zeros at the end of a number where there's a decimal point, then those zeros are significant. Now, if there's no decimal point, right, and you have zeros at the end of the number, then those zeros are not significant, right? So the decimal point makes a difference. So for example, in this case here, 1.000, the number of significant digits here will be 4 because you have a decimal point and these zeros are significant. In this case here, there are no decimal points, so therefore these zeros are not significant. So therefore this number has only 1 significant digit, all right? So that's basically the rule concerning trailing zeros. Okay, the next rule says leading zeros are not significant. So in other words, any zeros that comes before the first non-zero digit are not significant, all right? So in this particular case, you have 3 zeros here before the 3 here, right? That means that these zeros are not significant. Whoops, sorry. This 0 here, which is sandwiched between the 3 and 5, is significant. So therefore, the total number of significant digits here, represented in this number, is 3 significant digits, all right? Okay, so it's important that you know these rules so that you can answer the questions given down here. It says for each of the values below, determine the number of significant figures. So based on these rules, what would you say would be the number of significant digits for this first number here? 4, exactly. Because you have a decimal point and you have trailing zeros, and those zeros are significant. Okay, what about B?
3.
3 is correct. What about C?
1.
1. And what about D? 4, exactly. So those are the answers, all right? So it's very important that you know these rules because of what we're going to talk about next. And this has to do with how do you deal with significant figures when you're doing mathematical operations, right? And of course, you should know that there are 4 major mathematical operations. You have addition, subtraction, multiplication, and division, right? So whenever you're doing these operations on measured values, you have to make sure that you round off your answer to the correct number of either significant figures or decimal places to reflect the highest level of precision in the calculated value, all right? So let's deal with addition and subtraction firstly. So according to the rules for addition and subtraction, when you are adding and or subtracting numbers, you must round off your final answer to the lowest number of decimal places of the numbers involved in that operation. So if you look at this example, you're adding 1.003 to 0.2 to 0.001. So if you look at these numbers here, you see that you have 3 decimal places represented here. Here you have 1 decimal place. Here you have 3 decimal places, right? So basically, when you get your final answer, it must be rounded off to 1 decimal place, right? To the lowest number of decimal places of the numbers involved in the calculation. So basically, your answer will turn out to be 1.2, regardless of what you get on your calculator. In fact, let me do this calculation. Oh, shoot, I left my calculator. All right, let me use my phone.
204.
I'm sorry?
1.204.
That sounds about right. Let me just confirm that. think I left my calculator in the lab. Oh, well. So 1.003 plus 0.2 plus 0.001. Okay, so you're right. It gives you 1.204. So you have to round that off to the first decimal place, which is 1.2. All right. So that's what you do for addition and or subtraction, right? Okay, so that's the rule for addition and subtraction. What about multiplication and division? Well, according to the rules for multiplication and division, when you multiply and or divide numbers, you have to round off your answer to the lowest number of significant digits or significant figures, right? So in this particular case, we're multiplying 1.002, which has 4 significant digits, by 0.005, which has 1 significant digit. So the question is, to what extent you round off your final answer? And you round off your final answer according to the lowest number of significant figures involved in the calculation. In this case, that means you have to round off to 1 significant digit, and therefore the answer becomes 0.005. If you were to do that on your calculator, I multiply 1.002 by 0.005, you're going to get 0.00501. So the final answer would have to be rounded off to 0.005 to reflect that this would be 1 significant figure. So this is 1 sig fig here. This one is 1 decimal place here. And that's basically how you deal with that. So remember, just to recap, if you're adding and or subtracting numbers, you round off your final answer to the lowest number of decimal places. If you're multiplying and or dividing, you need to round off your final answer to the lowest number of significant digits. So applying that to these examples right here, let's look at A. We're dividing 5.0 by 0.31. When I did that on my calculator, I got 16.129 and a whole string of digits. So the question now becomes, to what extent do we round this off? Well, remember, for dividing and or multiplying, you have to round off to the lowest number of sig figs, right? So how many sig figs do we have represented here? 2 sig figs, right? And how many sig figs do we have represented here? 2 sig figs. So that means that we have to round off our final answer to 2 sig figs, which means that in this case, we need to round off to 16. All right, and that's it. Okay, what about B? We're multiplying 15.0 times 0.003. And this is what I got on my display, 0.045. But we have to take into account the sig figs. So how many sig figs here? 3 sig figs. And how many sig figs here?
1.
1 sig fig. So that means that you have to round off your answer to what?
0.4.
0.5 actually. 0.05 actually.
Or yeah, you round up.
So we round off to 0.05 as your final answer. Okay, let's look at this one. We're adding 1.003 to 0.01. So remember now, when you're adding and or subtracting, you're going to round off your answer to the lowest number of decimal places. So we have to look at the number of decimal places here, which would be 3 decimal places. And here, this would be 2 decimal places. So when I add 1.003 to 0.01, I get 1.013, right? So this is what I got on my calculator display, 1.013. So how do we round this off? To what extent do we round this off?
1.01.
Exactly, so this will be 1.01. Oh, by the way, something I should mention. Whenever you're doing these calculations, don't forget to include the units. For example, and I should have mentioned this before, in the case of A, the units here would be grams per mil, because you have grams divided by mils, right? In this case here, it's meters times meters, so that would be meter squared. In this case, you're adding 2 gram units, so this would still be grams. And then now let's look at D. In the case of D, we are subtracting 1.000. From that, we're subtracting 0.1. So the answer I got is 0.9 mils. And in this case here, we have 3 decimal places. Here we have 1 decimal place. So that means that this is correct as it is, 1 decimal place. So the answer in that case is 0.9 mils. Excuse me. And that's basically how you do that. Yes, sir.
For this, whenever we do our answer, do you want just straight equal lines, or do you want like estimated lines?
It doesn't matter.
Do you want a squiggly equal line or just a straight one for whenever we do like any touch of?
Oh, it should be an equal set because basically that's a practice when it comes to even after rounding off to the correct number of sig figs or decimal places.
Okay.
Yeah. Okay, any other questions about this? Any other questions? Any other questions? All right. Let me move on to molecular shapes. So basically, we talked about Lewis structures earlier, all right? And the key thing you need to remember about Lewis structures is that it basically shows how the atoms are connected to each other. That's pretty much all the Lewis structures shows you. It does not give any information about the shapes of the molecules, which is important when it comes to certain properties displayed by substances, all right? Now, basically, what they're talking about here is the fact that some radiation can affect basically how molecules vibrate. And when the molecules can vibrate at the correct frequency, then they will absorb that particular radiation. So as stated here, absorption of infrared radiation specifically causes molecules to vibrate, such as bending and stretching, right? Now, it's interesting to see that carbon dioxide and water vapor absorb infrared radiation, but nitrogen and oxygen does not. And as stated here, vibrations are related to the shapes of the molecules. So if we understand how molecules get to adopt a particular shape, then that will help you to understand why certain molecules will absorb infrared radiation and other molecules will not, all right? So let's talk about the shape of this particular molecule, methane, all right? The molecular formula basically gives you the composition. It doesn't say anything about how the atoms are connected. The Lewis structures, such as this one and this one here, shows how the atoms are connected. That's all it tells you. It doesn't tell you anything about the shape. Now, the actual shape of the molecule, of this molecule here, is what we call a tetrahedral shape, which looks like this. So this is a 3-dimensional representation of the methyl molecule, where these bonds are spread out evenly in a symmetrical way, such that each bond angle is approximately 109.5 degrees. And this is just basically showing you a space filling model for the same molecule, all right? So the shapes of the molecules is basically what helps you to make certain predictions as to the type of infrared absorption that will take place by the molecules. So there is a theory that is used to help to predict the shape of molecules. It's called the VSEPR theory, stands for valence shell electron pair repulsion theory. And basically what this theory says is that the bonds around a central atom will spread out to be as far apart from each other as possible, because the bonds are basically electron pairs, and electron pairs will repel each other, right? So in the case of a situation where you have a carbon surrounded by 4 hydrogen atoms that are connected by covalent bonds to those hydrogen atoms, the most stable arrangement for that situation would be the tetrahedral arrangement, which is what I showed you here, right? So this is the arrangement in the case of the methane molecule, where the bond angles are 109.5 degrees angle. Okay, so that's basically what happens in the case of methane. Now, here is a molecule which is kind of related to methane, but there are some important differences. One is that the nitrogen in the middle, which is the central atom in this case, is bonded to 3 hydrogen atoms, but it also has a lone pair of electrons on that nitrogen atom, right? So in terms of the electron pairs, they will be arranged in a similar way to methane. But in terms of the atoms themselves, the resulting molecule would be this shape right here, In some textbooks, they call it the trigonal pyramid shape, right? So as stated here, the electron pairs, the bonding and non-bonding pairs are arranged tetrahedrally, but the atom itself or the molecule itself is described based on, the shape is described based on the atom's positions, which means that the molecule of ammonia has a trigonal pyramid shape, all right? So that's what happens in the case of ammonia. And then now, if we look at water, where you have the central atom being oxygen, having two bonding pairs here, and two lone pairs here and here, it turns out that the shape adopted by the water molecule is what you see here, where the bond angle is 104.5. In this case here, we say that the shape of the water molecule is bent, or in some textbooks, they call it the V shape, right? So that's basically what happens in the case of water, all right? Now, in the case of carbon dioxide, the Lewis structure is this right here. And according to the VSEPR theory, if you have two bonds around a central atom and no lone pairs on that central atom, then these bonds will spread to be as far from each other as possible, which it means in this case that they will spread out to have a 180-degree angle between those bonds, right? So that's what happens in the case of carbon dioxide. So carbon dioxide is what we say is a linear molecule. That's a shape that we use, that's a term that we use to describe the shape, all right? So if you compare carbon dioxide to ozone, to water, you'll see that ozone and water are bent in shape, but carbon dioxide is linear. And the reason why carbon dioxide does not bend or does not have a bent shape is because there are no lone pairs of electrons on the carbon, right? The carbon atom has no lone pairs, while the oxygen here and the oxygen here, in this case, there's one lone pair. In this case, you have two lone pairs, all right? So that's why water and ozone is bent in shape, but carbon dioxide is not. Okay, so this basically summarizes the different molecular geometries that you will be concerned with at this level. There are actually more, but we won't get into the more complicated ones. So this is something that you need to be aware of. So let me try to explain what's happening here. If you have a central atom with no lone pairs, and you have two atoms bonded to the central atom, then the shape of the molecule will be linear, as you can see here. If you have one lone pair of electrons here on the central atom and two bonds, then it would have a bent shape, as you can see in the case of water. If you have three atoms bonded to the central atom and no lone pairs, then the shape would be trigonal planar. And when I say trigonal planar, I mean something like this. B bonded to Cl like this. So basically, these surrounding atoms will be at the angles of a triangle, and the boron will be in the middle. And the angle here, the bond angle here, will be 120 degrees. All right? So that's what the trigonal planar shape looks like. And then when we get to a situation where you have three atoms bonded to the central atom and one lone pair, then the shape would be pyramidal, trigonal pyramidal, as we saw earlier in the case of ammonia. And then finally, if you have four atoms bonded to the central atom and no lone pairs, then the shape adopted by the molecule would be tetrahedral, all right? So those are the common molecular geometries that you could have to deal with when it comes to your future assignments and tests and so on. So let's see if we can apply what we have just learned to this particular problem. The question says you're going to predict the molecular shapes, right? And basically, they're asking for you to sketch it. Now, I won't ask you to sketch anything. I've had some bad experience with the students with very limited artistic skills, so I'm not going to ask you to sketch anything. I'm going to ask you instead to basically state the shape, all right? So in the case of carbon tetrachloride, I could ask you, what's the shape of this molecule? The first thing you'd have to do is draw the Lewis structure, right? In fact, let me get out of this here. And let me see. Okay, so. Okay, so you're given carbon tetrachloride, all right? The first thing I would do is draw the Lewis structure, and we had some experience with that before, right? Carbon will contribute 4 electrons. Each chlorine will contribute 7 times 4 equals to 28. So therefore, the total number of electrons will be 32 electrons, which will be equal to 16 pairs. We put the carbon in the middle, surrounded with the chlorines. We put the bonding pairs first. 1, 2, 3, 4. Then we put the non-bonding pairs on the chlorines. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. All right? So that's the Lewis structure. In order for us to get a shape, we'd have to refer to this table right here. Right? And we have to look at, let me do this. Try to have both of them on the screen same time. Oh, okay. And then this one here. Okay, so this is the Lewis structure for carbon tetrachloride, right? So the central atom, which is carbon, has 4 bonding pairs, right? Which would be 4 here. It has no lone pairs, so that means that you'd expect the molecular shape to be tetrahedral in this case. Tetrahedral would be the shape of this molecule, right? So basically, if you're given the formula for a molecule, first thing you need to do in order to get the shape, to get to the shape, the first thing you have to do is draw the Lewis structure. And then based on the Lewis structure and based on the information provided in this table here, you can determine the shape of the molecule. While I'm at it, let me just show you in Canvas where what am I doing? Okay, this is what I should have brought over. Okay, in Canvas, there is a table that I've posted. You go to tables, and then you'll see, where is it? VSEPR theory, all right? And this basically summarizes the different shapes possible. Now, for all purposes, you'll be using this one, this one, this one, this one, this one, and this one. Don't worry yourself about the last 2 lines right here. So the first 3 would be what we will be dealing with. So in the case of what we just saw with CCl4, where the carbon is bonded to 4 other atoms and there are no lone pairs on the carbon, then that would be the tetrahedral shape. All right? So you'll have access to this table during your future exams, tests, whatever. All right? So let me go back to the PowerPoint and look at the next one, which is CCl2F2. So let's look at that one. So let me so the next one is CCl2F2, right? So again, we determine the Lewis structure. Carbon would be 4, chlorine would be 7 multiplied by 2, fluorine would be also 7 multiplied by 2. So this is 14, this is 14. So 28 plus 4, that's 32 electrons, which would be equal to 16 pairs. We put the carbon in the middle, surrounded with the fluorines and the chlorines. Doesn't matter where you put them, because we're not concerned about the shape now. That aside. So we put the bonding pairs first. 1, 2, 3, 4, then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So again, we have a structure where you have a central atom bonded to 4 other atoms with no lone pairs on the central atom, which means that it's going to be tetrahedral again, as predicted by the by the chart which I showed you, which I can't find for some reason now. Hold on. Oh, this chart right here. So again, it's going to be tetrahedral, central atom bonded to 4 other atoms. Okay, the next one is hydrogen sulfide, H2S. So let me get rid of this here. And here I'm going to write down the H2S. Hold on. H2S, all right? So we have hydrogen, which contributes 1 each, multiplied by 2, which gives you 2. And then sulfur, which is in group 6. And then we add that, we get 8 electrons equal to 4 pairs. We put the sulfur in the middle, surrounded with the hydrogens. And then we put the bonding pairs first. And then we have 2 lone pairs on the sulfur atom. So my question to you is this. What would you expect the shape of the H2S molecule to be? Bent, exactly, because it fits what we have right here, right? So the answer is that this would be bent, or you can say V-shaped, or you can say in some textbooks they call this angular, right? So any one of those terminology will work, right? So that's basically how you determine the shapes of molecules based on the Lewis structures. All right, any questions? Any questions? Okay, so as I said before, you can rest assured that I won't ask you to draw anything, but I will ask you to give the shapes of molecules. And I think that's pretty much, okay, hold on. Oh, okay, here's a question I didn't realize. Okay, this question says, using the same table and the strategies just described, predict and sketch, again, I won't ask you to draw, the shape of the molecules of SO2 and SO3. Okay, so let's do that one. So let me, let's deal with SO2 first. SO2. So we do the same thing again. S would be equal to 6. Each oxygen would be 6, and there are 2 of them, so we multiply that by 2. So that gives you a grand total of 18 electrons, which will be equal to 9 pairs. And then we put the sulfur in the middle, surrounded with the oxygens. We put the bonding pairs, 1, 2, then 3, 4, 5, 6, 7, 8, and then 9, all right? And if you remember, we said that each atom must have an octet, right? So you'll notice that the sulfur here will not have an octet because sulfur has 2, 4, 6 electrons. So what I will do is put that pair there, and that will give us S, double bond O, single bond O, and then lone pair here, right? So that would be the Lewis, some structure for sulfur dioxide. So now the question is, what's the shape? Well, let's go to the table. Where is it? Okay, there's the table. So here we have sulfur bonded to 2 oxygen atoms, and it has a lone pair. So which one of these would that situation fit? The central atom has a lone pair, and it's bonded to 2 atoms. Which one of these do you think it fits?
Trigonal pyramid? Trigonal pyramid?
Trigonal pyramid, no, because in the case of trigonal pyramid, the central atom is bonded to 3 atoms and a lone pair. This is bonded to 2 atoms.
Oh, then angular?
Angular, exactly. This right here. This atom here, the central atom, is bonded to 2 other atoms and a lone pair, which is the same arrangement here. So, therefore it's angular.
So it would be angular even though there's a double bond.
Yeah, right. Thank you for asking that question. Very important point. It does not matter the multiplicity of the bond.
Okay.
It could be a double bond, it could be a triple bond. It doesn't matter. That doesn't affect the shape. All right? Very important question that you asked. Okay, very good. Okay, so that's SO2. Let's look at SO3. So let me clear this. In the case of SO3, We do the same thing as before. Sulfur will contribute 6. Oxygen will contribute 6 times 3 equals to 18. 18 and 6, 24 electrons, which is equal to 12 pairs, right? We put the sulfur in the middle, surrounded with the oxygens. We put the bonding pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, and then we notice that the sulfur does not have an octet. So I'm going to put a pair of electrons down. So the final structure would be this. Okay, so in this case here, we have, oh, double bond. Oh, that's there, okay. So in this case here, we have the central atom bonded to 3 other atoms, right? So what do you think, based on the table, what do you think the shape is? Central atom bonded to 3 other atoms and no lone pairs on the central atom.
Trigonal.
Trigonal what?
Linear.
Planar, exactly. Which is this one right here. Central atom bonded to 3 other atoms, no lone pairs on the central atom. So therefore, the answer here is trigonal
Question.
planar. Yes, sir.
So why'd you rewrite it to the top oxygen have a double bond?
It doesn't matter which oxygen.
Yeah, but
But
why,
the reason why is because in this structure here, the sulfur does not have 8 electrons on its outer shell. It has 2, 4, 6. So you want it to get 8 electrons.
Okay.
So that's why I moved the pair of electrons from here to here. I could have just as well did this.
Yeah, no, it
Right.
slipped my mind.
Right, so that's the reason why. All right? Okay, any questions about this one? Any questions? Okay, so let me go back to the PowerPoint and see what next is up. Okay, so now we're going to get into the relationship between the between the shapes of the molecules and the type of interactions that the molecules will have with light or radiation. So basically, when it comes to the different forms of radiation can have different effects on molecular bonds. Now, as far as the UV radiation is concerned, it is energetic enough to actually break bonds, right? You can actually have the breaking of bonds between 2 atoms that are linked to each other previously. Infrared is not that energetic. It's not as strongly energetic as ultraviolet, but the effect it will have is that it will cause the atoms to vibrate around a central point in the bond, right? And then when it comes to microwave radiation, the effect that it would have on the molecules is that it would cause it to rotate, all right? So basically, the effect that the radiation will have on a molecule is largely dependent on the amount of energy that the radiation has, right? If the radiation energy is strong enough, it can cause bond breaking. If it is not as strong enough, it can cause the vibration around bonds. Or if it's not strong enough, even as strong as infrared, in the case of microwave, it causes rotational motion. All right? Okay. So one more thing I need to talk about before we end today's class. Electronegativity, a very important quantity. It is basically a measure of an atom's ability to attract shared electrons or electrons that are part of their bond, right? So it's kind of like a pull or tug of war that both atoms sharing electrons will have. If one atom is more electronegative than the other, then it will have a greater attraction for the shared electrons, right? And a guy by the name of Linus Pauling came up with a scale, and based on it's a 4-point scale, and I need to get out of this and show you what we're talking about here. Let me bring down. Okay. Um, What am I doing? Okay. Okay, so I'm going back to tables here again. And I'm going to go to tables chemistry. And there, I think this is the last page in this document. So let me just scroll all the way down. Okay, so he came up with a 4-point scale. And this table here basically summarizes his efforts in terms of attaching a number in terms of representing the electronegativity of different atoms, right? So basically the numbers that you see there are the electronegativity values for the respective elements, right? So for example, for nitrogen, the electronegativity value is 3.0. For oxygen, it is 3.5. So basically what that tells you is that oxygen is more electronegative than nitrogen. So what that means is that if oxygen were to share electrons with nitrogen, the oxygen will have a greater pull on the shared electrons, and therefore the electrons on average that are shared between the two atoms will be on average closer to the oxygen than the nitrogen. All right? So that's basically what this is telling you. You have a question?
So is there a reason why the complete set of valence electrons is not on there, like for the electronegativity?
Why what?
Why like group 8 is
Oh.
on there, group 8A?
Very good question. And that has to do with the fact that in group 8A, those elements have no attraction for electrons whatsoever.
Okay, so
Very
if it's
limited.
complete, they don't
So
need.
therefore, we don't even consider them in most cases.
And then why is hydrogen greater than lithium or beryllium?
Because hydrogen is a nonmetal and the other elements are metals. One general trend is that metals tend to have low electronegativity values compared to non-metals, all right? It's a lot more involved than that, but that's just basically a simple way of explaining it. Metals tend to have a lower electronegativity values compared to non-metals. Okay, so this is the table that Linus Pauling came up with, and this will become important in certain problems that we'll be looking at shortly. But there are certain trends that you can observe in terms of going across a period and up a group. What you'll find, let me go back to the table. What you'll find is going across a period, any period, you'll find that the electronegativity increases, right? And going up a group, you'll find the electronegativity increases as well, right? So that's why, going back to the PowerPoint here, you'll see that they have this arrow pointing up at an angle like that, showing you the general trend in terms of the change in electronegativity going across a period left to right and going from bottom to top of any group, all right? So that's basically the trend in electronegativity in the periodic table, all right? Now, as we said before, the more electronegative atom will have a greater pull on the shared electrons, and therefore, as a result, the electrons that are shared will on average be closer to the more electronegative atom. The consequence of that is an accumulation of negative charge on the more electronegative atom. So in the case of carbon dioxide shown here, for this bond, the oxygen will pull these electrons more closer to it. So therefore, the oxygen will have what we call a partial negative charge. Not a full negative charge, but a partial negative charge. For the same reason, this oxygen will have a partial negative charge as well. And in the case of the carbon, it will have a partial positive charge, right? So basically we say, the term that we use here to describe this situation, we say that this bond is polar. So we say that this bond is polar. And the same is true for the other bond, because you have a separation of charge between the two atoms sharing the electrons, all right? And that's because the oxygen in this case is more electronegative than the carbon, right? So that's the reason why we have that separation, and therefore the bond is said to be polar. Now, it says here that as the bonds are stretched or bent in a molecule, the charge distribution of the molecule be affected, and therefore, as a result, you can have absorption of radiation. Now, it says here that if the geometry and direction of the stretching, bending, cancel discharge redistribution, then the infrared radiation will not be absorbed. And I think the next slide is going to show you what is exactly happening in that situation. So let's look at these possibilities of the different types of vibrational modes for the carbon dioxide molecule, right? So in this case here, carbon in the middle, two oxygens, right? And basically what is happening here is that you have the two atoms, the oxygens at the end, going back and forth like this, right? Basically, in that particular situation, there'll be no change in the electron distribution, right? So therefore, as a result, there'll be no IR absorption occurring, all right? However, in the case of B, C, and D, there'll be a net change in dipole because if this bond is shortened and this bond is lengthening, that means that the dipole overall or the charge distribution overall will change. The same is true for this one, the same is true for this one. So therefore, in these situations, absorption will take place here, absorption of radiation, absorption. Same is true for this one. Same is true for this one. But in this one, in the case of the first one, there'll be no absorption because the vibrational mode or action is uniform and symmetrical. Yes, sir.
Wouldn't C be symmetrical as well?
What's that?
Wouldn't it-
See? No, not exactly.
Or is it because it's the center atom is also moving?
Exactly. The central atom is moving down and the two oxygen atoms are moving up. So the result is not a symmetrical.
So if the center atom didn't move, then it would be no absorption.
I think it would still be unsymmetrical. The only one that's symmetrical among these four would be this right here. Because the two atoms at the end will be going like this.
Okay.
See what I'm saying? So in that case, there'll be no net change in the charge distribution in the molecule. So this one, and this one will result in IR absorption. This one will not, all right? And this is just basically showing you a graph which basically plots percent transmittance versus wavelength in micrometers. And basically where you have the absorption, where you have the transmittance falling, that corresponds to absorption. And in this case here, you have the absorption peak here, which is related to asymmetric stretching, going back to this here, which would be this right here. This is asymmetric stretching. And then in this case here, this is talking about bending, which is related to this one here and this one right here, all right? So that's what happens in the case of carbon dioxide. And this is showing you the transmittance of water, I think, right? The absorbance, the spectrum of water. And it's a bit more blurred because it's in a liquid state, really. But again, you see the absorption peaks here and here. Okay, that's all I'm going to say for now. This is just having some information about greenhouse gases and in particular carbon dioxide and other related stuff. You can read that on your own. So what time is it? It's now, okay, 4 minutes to 3. So concerning your test on Monday, will be based on the first 3 chapters. And basically, if you review the assignments, and I've posted the assignment keys. I don't know if you noticed that. I've posted the answer keys. Let me show you where. So if you go to, if you go to files and go to assignment keys, you're going to see 3 folders containing each assignment, right? So this is the answer key for assignment 1. Right? So I would recommend that you just review them. If you have any questions, feel free. And as far as the setup for the exam is concerned, I think what I'll be doing is making it 3 questions, a question per chapter. But each question will have different parts, you know, like A, B, C, whatever, so. Yes, ma'am.
So all of the tables on there, where you said we could use the tables.
I'll provide the tables.
Okay.
I'll bring copies.
It's
I'm
not,
gonna bring the tables and I'm going to provide an extra sheet of scratch paper for you to work with.
so it's held in this class.
Yeah,
Okay, so it's not like we have to go to like building 5 and,
no, you mean like a testing center?
sure,
No. In fact, they only allow testing for either online classes or hybrid classes, so,
really, wow.
yeah,
No, I know that.
which was kind of disappointing to me, but that's, I guess they get overwhelmed if everybody decide to, you know, send their test over there, so.
It's so confusing to take a test.
What's that?
So confusing to like set up a thing because it'll tell you how to do it, and then you go in, they're like, whenever.
Oh,
I
you
did
mean
it-
like you have to settle your appointment and so?
Yeah, whenever I did it, they're like, we don't see your name, and then I see my name, I'm like, well, I'm right there, and they're like, well, that's not for here, I'm like, it says Ocala. They're
Oh,
like, oh, well, then I guess we'll have to fit you in, and I'm
But-
like,
that's strange because whenever I send, because like right now I'm teaching a hybrid course.
yeah,
And all I have to do is send the test to an email for the testing center.
yeah,
And any one of my students can go to any one of the testing centers.
yeah, it was so weird just how they had it structured and set. It made me not want to do online. Or hybrid.
Yeah. Well, unfortunately, you have to do it here, so in class,
I'd rather have that.
yeah. All right, so I don't know if you guys have any questions about the test or any particular topic that you need further explanation on.
Could you do like a quick review of chapter 1?
Okay, if I
Or
remember
at
correctly, chapter 1 dealt with,
Because I wasn't here for that set.
oh, okay.
Class.
So basically, chapter 1, I started off with because
Yeah,
well, you weren't here, but
Yeah.
I was telling the rest of the students that I don't like how the textbook set it up, because I believe that the first thing that we should talk about is what is chemistry, the scientific method. So that, I did that, so you won't find that in the text.
Okay,
But I did that, and this first assignment basically covers that. So basically, I talked about what chemistry is, which is the study of matter and the changes it undergoes. I talked about the fact that in chemistry, we are concerned with the structure, we're concerned of matter, we're concerned with composition, and what else? The defining characteristics. And there's one more thing, I don't remember exactly right now, but anyway.
so kind of just go through that.
Right, exactly. Yeah, this
Keep
basically
going.
covers what I went through on the first day. I talked about the scientific method. I talked about the fact that, you know, there are several steps involved.
You have like the definition of physical and chemical change on there as well, just so I have it.
Maybe in the PowerPoint, but let me see here.
Do we have to know those definitions for the test? Like,
Well, at least if you can explain it in your own words, that would be fine.
So as long as it's like the general idea of what it is.
I was gonna say, because if it's like textbooks needed, us
Right,
going
and
over.
then we talked about physical and chemical changes. Physical and chemical properties. What else?
Compound element and
That's
mixture.
right, know the difference between element, compounds, elements, compounds, homogeneous mixtures, heterogeneous mixtures. And what else?
But you have that PowerPoint though. Go
I
through.
think so, yeah.
Okay,
And then we talked about scientific notation, converting from one unit to another. You know, atomic number, mass number, all that good stuff. So that was the first chapter. And then let me see here, just.
that's it. I was here for chapter 2 and 3.
Yeah.
Everything else.
Yeah, so just review, I would say just review those assignments.
Okay,
You should be in good shape if you do that. Yes, ma'am.
so ammonium is NH3, right?
Ammonia,
Ammonia.
NH3. Ammonium is NH4 plus.
Okay.
Right.
Are we turning in the chapter 4 today?
I'll collect it, yep.
I have-
I need a vacation
I
already.
haven't even put away my stuff in your head.
Okay, folks, and of course, if you have any questions, I'll be available during office hours. You can consult. The syllabus tells you what time and where I'm located. Thank you. What this would right here.
Nope, 9. Yeah, that doesn't matter, order for that. Okay.
Final order.
The only thing that matters is that those compositions stay together. The bigger binder ones can stay together. You are gonna have to hold all this. I'm drinking more. There you go. I mean, I can shotgun this.